trying to keep things normalized, it just doesn't, like, you're not able to support very low standard deviation values.
Oh, okay, it sounds interesting. Like maybe was there like a particular like library you were working with, or maybe like, or yeah, you mentioned you didn't remember exactly what the objective function was, but like what like yeah, I guess I'm just kind of curious about your methodology. Like, how do you approach problems like this, or what tools do you use? Maybe.
Uh, this was with PyTorch.
Uh huh. Gotcha. Okay. Okay. Cool. Yeah.
Hey, Max, I had a different kind of question for you when
Uh
you're
huh.
ready for that.
Yeah.
Um, Related to chapter 24 and spice,
Hmm.
um, how much of what is in chapter 24 could be like simulated in spice
Hmm.
and and proven that way? I'm wondering, like, if people here think it's completely theoretical and not provable, and if Spice would kind of talking about how you approached validating your archive paper using
Hmm.
Spice might help with that.
Right. Yeah. So what I would say to that was, so yeah, just for a little bit of background here for people who aren't as familiar, Spice is just yeah this big open source library, big open source software package for simulating electronic circuits, and it has some support for simulating noise in electronic circuits. And so what we did in this last paper we wrote, thermo Bayesian inference, was we designed circuits to sample from like Bayesian posteriors by running a kind of Monte Carlo algorithm. And the noise in that, we were able to simulate those circuits in Spice and introduce noise into the circuits using kind of the available framework within Spice. And we were able to show that we didn't, in fact, sample from the right distribution after we let it run for enough time. So I think that basically the problem is when you get to more and more complicated kind of distributions that you want to sample from, it's difficult to like come up with circuits that do it, because we don't really have like any kind of like any generalizable framework for doing that. Like the circuits we were able to come up with that in that paper were really come up with by like guess and check, and we don't have like a framework for how do you in general design a circuit that samples from a given distribution, or in other words, how do you design like an energy function that you want. um, so I would say that the thing where the place where you get stuck in trying to apply spice to simulating or to like demonstrating these results wouldn't be like the limitations of spice itself as a software, but the limitations of like how do you design the circuit that actually implements that energy function, I think.
Gotcha. Good to know.
Yeah. But I also think that's a really interesting kind of research question. It's like, is there a general approach to designing circuits that have a desired energy function? Is something we don't totally know yet, but yeah. So yeah, I'm kind of curious about this figure 24.1 actually. I haven't really looked at this yet. Um, it says combining two energy functions in 2D by summation, which is equivalent to multiplying the corresponding probability densities. Do people see this figure 24.1 in the book?
I'm not able to. I think 24.1 for me might be a little bit different. I see section 24.1, 24.1.1.
Yeah, so that's a example product of experts. Is that right?
Yeah.
Okay. And then right above that, is there a figure that in the caption says figure 24.1?
Hmm.
Okay, okay. Yeah. Okay, so this is a nice figure. So because I think that well, I'm not sure if what's being plotted is the energy or the density. I guess it's supposed to be the energy that's being plotted here. Um, let me see. Yeah, I think it's the energy. Okay, so right. So if we think of like energy A, yeah, so I really like what they did here because they show the trajectories actually. So if you look at figure, I guess the bright points are really the low spots. So is this like the negative energy maybe? Um,
I think it makes sense either way.
Well, okay, so yeah, so the thing, so if we think of those trajectories, like usually what like those black lines, what those should do is those should go in kind of the direction of like high energy to the direct to low energy. So we could think of it as like the bright spots are actually high energy, but in that case, like all the trajectories are starting from the high energy points already, which is kind of strange because usually you don't know where the energy is high or low, and you just kind of start trajectories from random points, and then they end up in the low energy points. So I would expect that like the bright spots are actually the points with low energy, and then kind of the story here, if we look at the left panel, energy A, is that you've like chosen random points to start the trajectories, and then they've all kind of gone towards low energy points, if that makes sense.
Yeah, I think one nice symmetry might be that when you are doing optimization, you can choose whether you want to optimize like up or down.
Yeah, yeah, that's true. I mean, just like from the point of like the notation, like you like the energy function is usually, or yeah, pretty much always the thing that is being minimized. So you think of it as like an objective function that you want to minimize, kind of. But yeah, so I think what's going on here is that the bright yellow spots in this plot are the lowest points in the energy landscape, and so these trajectories are kind of starting from random places and then going towards those bright spots, which are the low energy points. And then energy B is like a different potential energy function, and you can also run some Monte Carlo simulation to sample from the distribution associated to that energy. And then what they've done is they've just added those two things together. And so on the rightmost plot where you have energy A plus B, um, it's well, the other 2 points that were low energy and energy A are kind of washed out, and really we only see kind of the right 2 points that were the kind of low energy for both of the
Uh-huh.
distributions, if that makes sense.
It's interesting. They're smooth points from the bright to the light spots, or the vice
Mhm.
versa.
Right.
So the reference paper that is referred for that figure, I think it's by you. I forgot his name, but it
I'm
says that the dynamics used is Langevin dynamics.
It's not by me. Oh, the person's name is you. Are we doing like who's on first
Yeah,
here?
yeah, you. Sorry,
Okay.
I didn't mean YOU. His
Okay.
name is Yulian Yu and Igor. So if you refer to their paper, it's implicit generation and modeling with EBMs. So he's referring to the sequential combination through Langevin equations. So the basic addition is through the stochastic differential equation.
Okay, great. Okay, cool.
Yeah.
Yeah, yeah.
So that's the basic. Yeah.
Okay. Yeah, okay. That's what I would kind of assumed when I saw the picture and I saw these trajectories. That does exactly look like using Langevin dynamics to sample from, yeah, like from an energy-based model. Okay. Okay, yeah, I pulled up this paper. This seems like a cool one, actually. Let me post this as well. And what do people call this? Like the nest or something? I don't know.
Which one?
I'm just going to post that paper by Yuan Du and Igor Mordach, implicit generation and modeling with energy-based models. Let's see. Oh, I actually don't see that figure in the paper. Oh, I do. I see. Yeah, it's figure 14.
Yeah,
Hey,
it's 14.
hey Max.
Yeah.
Next time you start a space, start it from your phone,
Oh,
and
yeah.
then join from your laptop so that you can have comments. Because I don't know why, but it's so much easier to get get links and stuff off the comments than the jumbotron. And plus, um, the replies are sticky; they last after the space is over. Whereas I think these Jumbotron things are going to die after the space is over. At least I don't know how to get to them then. But anyway, just a tip for next time.
Okay, I see.
Just remember, start from your phone.
Okay, good to know. Gotcha. I see. Okay. Yeah. Although I am putting stuff in the comments, so hopefully those will also still be persistent. But yeah. So.
Oh, you have comments to this space?
Yep. It's just the post where I.
I'm curious why these figures are, why they have a shape. Where does that shape come from? Hello?
I can hear you, but I can't hear anyone else.
Yeah,
Oh.
I can hear you all. I don't think Max is speaking, but his speaker is on.
Hey there. Can you hear me now? Okay. Yeah. Yeah. Sorry. I actually accidentally I tried to post something in our group chat and accidentally left the chats or left the space. So, but yeah. Yeah.
Yeah, Max, I was wondering where the shape of the. I wonder where the shape for these images come from.
Sorry, what page are you looking at to make sure I'm following?
I wasn't following the other equation, but I'm still on like the other figure.
The figure from the book, I think, which was let's see, figure like 4 or 24.1 or something.
Oh yeah, are we on 14.1?
Oh, that's right, 14.1. Sorry. Yeah, let me find that again.
I was on 24.1. I bet I wasn't. I can't find it.
Yeah, it's a big book. It's hard to find stuff in here. Let me just. Okay, so it's energy-based models. It's figure 24.1, right? So, but yeah, sorry. What was the question you had though?
Oh yeah, I was just wondering. Shoot. Oh yeah, where do the shapes of these images come from? There's like embedded like circles, and there's like a rectangle.
Oh, like whether like those distributions actually correspond, or like, are you asking like what the shapes represent in the picture, or like do they come from a particular, like solving a particular problem, or what? Yeah, what do you mean by that kind of?
Yeah, I guess both.
Okay. So what they represent is the energy function, I believe, in equation 24.1. So remember, at the end of the day, what we want to do in a generative model is we want to sample from some distribution, and we want that distribution to be similar to the distribution of our data. So like if you think about the problem of like image generation, you have a bunch of samples from the data, like you have all the pictures on the internet, for example, and then you want to be able to train a model that can sample from that same distribution. In other words, generate an image which is like seems like a typical image you would find on the internet or something like that. So the energy function is a way that we describe a distribution, which is like it's basically just the log of the distribution. And I think that that's basically what's being plotted here as a heat map. Is so here like the distribution is over two variables, x and y. So when you draw a sample from that, you would get a sample of x and a sample of y. And basically the energy is like this function E of x and y, and we're plotting that as a heat map, that function basically. and we have two different ones, energy A and energy B. Does that make that kind of make sense?
Yeah, yeah.
Mhm.
It's interesting. The log effectively here, if these values in the heat map are like the values of the probabilities from some equation, if you were to apply the log to that, it would effectively dim those distributions a little bit and make it smoother for those paths to move towards those lower energy areas.
Right. So the thing I'm not 100% sure of is whether they're plotting the energy or the log here. But I think they're actually, or yeah, whether they're plotting the distribution P or the log of P, which is the energy. I think they're plotting P actually, which is the distribution, and not plotting the energy. And the reason why I think that is that if you look at like the spaces in between the dots that are all very dark, there doesn't seem to be much of a gradient there, right? Like it looks like it's constant. And if that were true, then your gradient descent, wouldn't work very well. And so, as you said, gradient descent on the distribution itself, it's really gradient ascent, or you're going up on the distribution itself. You're trying to go towards the points with higher probability, but it wouldn't work very well because if you think of a Gaussian, which is like one of these dots, can basically be thought of as like a Gaussian roughly in 2 dimensions. For a Gaussian distribution, it's out when you're outside of 3 or 4 standard deviations, it's basically 0. If you take the gradient of that, the gradient also goes to 0. But if you look at the log of the normal distribution, it's a quadratic, so it has a nice kind of smooth gradient everywhere. So I think basically they're plotting here the probability density, but you're actually doing like a gradient descent on the energy, or like the log of that density.
Yeah.
And also, when I just want to make a quick note, I think it says that most of these models do not assume the Markov assumptions. So one would be the probabilities are constant over time would not be applied. So I think the biggest problem is how to track those integrals. And it says if those are intractable, we have to go through those suggested methods, since we don't have these Markov assumptions to go forward with.
Mm-hmm. Oh wait, yeah. Where do they talk about the Markov assumption actually?
It's right there at the start. Hold on.
In Kevin Murphy's book?
Yeah, it's a book 2, near the 24.2. It says that ABMs do not usually make any Markov assumptions, right? So I was trying to go through to see how they do the integral, but they do declare that it's intractable. So that's why we are going through these hoops to keep track of the integral, since we do not have any Markov assumptions.
I'm not seeing that. You said it's near 24.2 maximum likelihood training, or yeah, where is this stuff about the Markov assumption?
It's right next to 24.2, where the partition function is defined. If you go to the next, yeah.
Okay. I see. Oh, I see. Since EBMs do not usually make any Markov assumptions, evaluating this integral is usually intractable. Consequently, oh, I see what they're saying, I think. Okay. Yeah. I think that let's see, what would that mean?
So just to put a pin on what we're talking, there's one assumption that's very important, is the probabilities are constant over time. This is one of the assumptions that would not apply. So
there isn't any notion of time here yet. Like, we're just talking about a distribution over many variables. But I think that what they mean by a Markov assumption is that, like, let's say that you thought of all the different components of the vector x as like each one of those has an index I, and maybe you could write the distribution as basically in the form of a Markov process, where you think of like the index of the coordinate, like the coordinate as time, kind of. And so like the probability is like some probability of p of x0 plus p of x1 times p of x, or given plus p of x0 times p of x1 given p of x0 times p of x2 given p of x1. I think they're saying like you could assume that the distribution factors like that, maybe.
I see. So for image generation, there won't be any time factor in
Yeah.
like a physical time. It would be an artificial way of giving the bound.
Right. There's no way of kind of assuming some like conditional or there's no way of basically writing as a graphical model. I think is kind of the point here, is that like sometimes you have a bunch of different variables, but it's not that bad because all of those variables have kind of causal relationships, and so you can draw some graphical model. But in general, when you have a bunch of different variables and they don't have any obvious causal relationships, and you can't draw like a graphical model that's useful, then it's going to be very hard to evaluate this partition function, basically.
Right, but I was trying to form some sort of analogy where we are using Langevin equation, which is stochastically dynamic, with respect to temporal dv by dt.
Mm-hmm.
So we are taking away that particular part and saying it's not going to be temporally important, but we want this particular dynamics in our distribution, probability distribution, that is.
So I think so we need to think of these things separately as like, what are the properties of the distribution we want to sample from versus how are we going to sample from it. So Langevin dynamics is like, it's like a way to sample from the distribution we want to sample from using a Markov process. It has a time coordinate. It is a Markov process, but at the end of the day, we just get samples from this distribution. Now,
Oh, I see. Yeah.
he's not saying that doesn't work. We can still use that Markov process to sample from the distribution we want. What he's saying is that for some distributions, it happens that it's very difficult to use any other method. It's very difficult to get the partition function or the normalization factor, because some distributions don't have any natural causal relationship. If you have a random vector with 100 components, but those components are at different points in time, then there's like this causal relationship where components at a later point in time are determined by ones at an earlier point if you make this Markov assumption. But in general, like the pixels in the image don't have any like natural graphical model like that, I think is the point.
So why are they assuming the delta of the log of z theta? Why would they assume that that's 0?
Where would they assume that, or what do you mean?
I think 24.2, right, in the MCMC area.
Are you talking about equation 24.2 or like section 24.2?
Oh, 24.17. I thought we were on section 2.
Section 24.17. I'm trying to find that.
Yeah, the equation is 24.17.
Oh, 24.17. Okay, I see. Yeah. Okay. Oh, I see. Why are they saying minus grad x of log z theta equals 0? Good question. Let's see. I'm not sure at the moment, actually. Yeah, so this is probably something we'll get back to next week after we've read this more closely. But that does seem like an important thing to know. I think I know, actually. Okay. Yeah. Okay, because the partition function, the normalization factor, isn't a function of x. So if we go back up to equation 24.1 and 24.2, there's two things that depend on x, which are p theta and e theta. Those are functions of x, or in other words, the thing that we sample, that we get samples at the end of the day. But z theta is found by taking an integral over x, but itself isn't like a function of x. So that's why they're saying like the derivative with respect to x of z theta is 0.
Oh, I think I got a little lost there. 24.1.
Yeah. So like the idea of a normalization factor is it's a constant that you multiply your distribution by, so the distribution is normalized, right? So that constant doesn't depend on X. That's what
That's Z.
Yep,
And
exactly.
then that would be applying the law here.
Right.
Okay.
Now it can change. It does depend on theta, which is actually important, but it doesn't depend on X. So that's why they can get rid of that term.
Gotcha. Interesting.
But yeah, I don't know. Let's see. Any other kind of general ideas or questions about EBMs at this point? I think we'll have a lot more to say about it next time when we've actually read the thing. But yeah.
Yeah, I pretty much only have questions.
Yeah. By the way, I saw Christoph is here. Hey there, how's it going, Christoph? But yeah, any questions are good too. I can try to answer them. Other people might have answers, but we can always think about them. Yeah. Hi, Christoph. Can you hear me?
Hey Max, how's it going? Sorry, I just joined, so I'm a little bit lost.
Oh, sure. Yeah. Well, yeah, we're just talking about energy-based models, chapter 24 in this book by Kevin Murphy. Were you able to find the link to the book?
Oh, yeah, I got it, I think.
Nice.
Chapter 24.
Yep.
I only see 23 chapters in mine.
You wait, really? Do you have the right book or?
Maybe not. Probabilistic machine learning. Oh no, this is the book by Bishop.
Yeah, no.
Sorry, wrong book.
Okay. So this is Probabilistic Machine Learning Advanced Topics by Kevin Murphy. But yeah, the link
got it.
Yeah. But yeah, while he pulls that up, it's basically just kind of at this point like introduction to energy-based models and gives a few examples of where they're used and stuff like that. But yeah.
Cool. I was actually thinking about probabilistic energy-based models last night. But from a rather different angle. Like if you observe an agent running around an environment doing something, how can you efficiently store and kind of like dynamically create kind of an energy-based model that would be capturing the sort of objective function of the agent in terms of minimization of free energy. Because the problem is that the agent running around in the environment, is growing in the environment. It's growing in that environment. It's acquiring new experience, and you somehow need to incorporate that into the model. That as you go around and record what's happening in the world, the kind of like it has to shape the EBM of the agent, and then EBM that EBM could be used to sample for the next action. And I have a really interesting idea of how to sample from that EBM efficiently.
Okay.
Basically, turn it into a very precise optimization problem, but very, very precise. So yeah, it's I think EBMs, are going to be a lot more important in the near future than they've been so far. Like this generalization, I think is actually quite profound. The reason why this stuff works, like the reason why this stuff works is like it seems pretty weird, like that you can basically geometrically describe everything about the world. It's a very, very strange proposition.
Mm-hmm. Well, I think that you're really gonna like that some of the topics that that we're going to focus on, because yeah, the two things I really wanted to hit from this book were chapter 24 on energy-based models, and chapter 34, which is decision making under uncertainty, or exactly the problem of like how do you make an agent that makes decisions under uncertainty, and like how do you train it's how do you learn a good policy, etc. And I think there's probably some interesting like intersection between between those, kind of as you were talking about, because like with all this like explore exploit stuff, you want your agent to like make random decisions sometimes using like Thompson sampling or something. But I haven't actually, yeah, that's something I haven't actually read about, like using EBMs for agents. But it sounds like something interesting for sure.
Well, I think this is the way we can basically take the insights from active inference and actually apply them using the methods of deep learning. Because energy-based models are basically a perfect, class of models that sits in between the two. Active inference is a little bit difficult to implement directly. It's kind of a little bit too atomic, the way that it's been done so far, and it's a little bit, and we don't have in active inference, sort of community, they don't really have any means of discovering structures of generative model. It's more like someone has to sit down and write one, come up with a model a priori. So there's this, God's eye view, and you want to somehow be able to, construct that model dynamically or derive it from data, like in the case of the deep learning system. So I think it will be very productive for agents to essentially use EBM to do free energy minimization, and kind of like just use the EBM to model that somehow.
I see. Cool. Yeah. So that actually makes me think about a question that I just kind of wanted to pose to everyone, and I think we've touched on it a little bit, but it's a question I think is, it doesn't have an obvious answer, but I think is an important one, and I'm really interested in it, which is like, why is it that energy-based models, that it seems to be useful to think about probability distributions in terms of energies outside of the context of statistical mechanics? Because it clearly makes sense in statistical mechanics, where we think of like the energy as kind of being the cause and the distribution as being the effect. Like really the energy is the more fundamental thing, and then we observe this distribution. But in machine learning, that doesn't necessarily seem to be the case. So I'm just kind of wanted to pose that question, see if anyone had any thoughts of like, why is it useful to think about probabilistic machine learning, or just probability distributions in general in terms of energy functions?
So this is what I was talking about just a moment before, right? Like that this unreasonable effectiveness of geometric modeling. An energy-based function is simply kind of optimally parameterized function for representing some kind of arbitrary geometric shape. There's something I bet there's something to it related to, for instance, the class of rapidly decreasing functions, Schwarz's class of rapidly decreasing functions that he used to put Fourier transform onto like solid mathematical foundation, so it actually converged at the end of the intervals and stuff like that. So exponentials are, it's a very, very, very special, very, very, very privileged class of basis functions. So with that, you have essentially something that gives you an arbitrary geometry. You can model an arbitrary geometry with that, given enough parameters, right? Because your exponentials are kind of like infinitely smooth. The exponential is just that's kind of like this optimally curved function, right? at all points is its own derivative. And so that seems to be the case. But why does it work? Now, like I have an answer, but it's a little bit wild actually, and it essentially is the resolution of the question of like how we connect quantum theory to general relativity. right?
So
Like
actually, before you go into that, I just wanted to get into this. I think you said something really interesting about this like Schwartz spaces of functions, and I just wanted to understand that point a little bit better. So I'm just kind of curiously searching on Wikipedia here to follow along. But so as I understand it, so these this is like Schwartz spaces are kind of a spaces of functions with rapidly decreasing derivatives. And it says that the Fourier transform is an automorphism on this space. In other words, if you take a Fourier transform of a function with a rapidly decreasing derivative, you get another function with rapidly decreasing derivative. So I guess in one sense that doesn't surprise me hugely, because I know that for example, Gaussians have this important property that when you take a Fourier transform of a Gaussian, you get another Gaussian, and they seem to be functions with rapidly decreasing derivatives. And maybe this is like a generalization of that idea. And I was wondering, like, this seems like a pretty deep insight that this might be related to like the utility of energy-based models. And I was wondering if you could expand on that, like why exactly is it important to have this kind of automorphism or like closure property under Fourier transforms?
I think the inestimable Terence McKenna said it best when he said that nature is self-similar across scale. When you are modeling natural phenomena, you are going to essentially encounter fractal patterns. So you have to have this class of functions that gives you this, composability. But there's also exponentials have a lot of special properties that are related to physics. For instance, it took me like 10 years to unpack this statement. One of my lecturers used to say that exponential functions are eigenfunctions of linear time invariant systems, and that enables interstellar communication. And it's a wild statement, but it's...
Yeah, I followed the first part of the statement. I'm familiar with the first part, but yeah, the second part was a little bit, I don't quite see the connection yet. So yeah, definitely interested to see where this goes.
The reason this enables interstellar communication is basically that if you exponentials ripple through differential operators unchanged, right? They may be scaled, but they're still exponential. So if your signal is exponential in nature and ripples through a linear time invariant system, then it's going to remain unchanged in its causal structure, but it may be rescaled. But what are the differential operators that it encounters? Well, it's just rippling through effectively a linear system physics, right? We treat physics in a way that at some point we always say like, well, at this point I am basically linearizing. This is how I define the neighborhood where I'm happy to do that. And this Schwartz's rapidly decreasing function stuff, I think it gives you this kind of composability at every, like at the level of derivatives and so on and so on, because you get this automorphism property. So you always have derivative of derivative of derivative of derivative, and you want to have this kind of smoothness that allows you to effectively represent an arbitrary manifold. Something like that. I can't explain it, more precisely. I only kind of understand it in terms of ideals these constructs represent. But I'm somewhat confident about this part.
Okay, I think I understood a little bit better the thing about interstellar communication, maybe in that, like, I guess if we imagined like a universe where there were no eigenfunctions to the kind of time propagator of a linear time invariant system, then it would be very hard to have anything kind of persistent, like any kind of persistent signal, because it would always kind of, anything you put in would kind of decay or be changed to the output. So the fact that like LTI systems have this class of eigenfunctions allows you to like use them to represent information. But the thing I'm still confused about with the composability thing you were saying is that like this like property that like taking a Fourier transform of a function in this class gives you another function in this class doesn't, to me, like suggest any obvious operations to compose together, I guess. What are you kind of like imagining there? What do you have in mind there in terms of composability? Like what is actually being composed?
Well, you know what was the problem with Fourier transform before, and why I don't know why Schwartz actually worked on this specifically, but the problem with Fourier transform that was unaddressed until this point is that Fourier transform didn't work, exactly. It just simply didn't converge in a lot of fairly simple cases. Like, for instance, if you have a step function, Fourier transform does not converge at the end of the interval. So there were these cases where we couldn't represent functions precisely. Also, Fourier transform of the Dirac delta, the argument of what it is has been the kind of hand wavy. Well, infinitesimal number is a very, very small thing, kind of thing. Wave your hands, and you have a derivative. So Schwartz comes along and he's like, well, I'm going to make it actually precise. Like, precise. What are the conditions? What is the class of functions that is necessary to make it actually work so that it just adds up everywhere? And that's the class of rapidly decreasing functions, which happens to be exponential because they're just like optimally curved.
Yeah, and I think the goal behind trying to normalize like a PDF after it comes out, you like you're kind of trying to offset that growth towards Dirac. Like when you get to a very, 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 very low standard deviation and your model starts getting like really, really peaking really, really fast. In the PDF, without normalization, it will like bound to infinity, or like it'll diverge to infinity. You'll get like this.
Yes.
You'll basically just get the Dirac, right? But it's pretty much just like an asymptote because you can't divide by zero, right?
Well, that's the thing. But with this formulation using Schwartz's generalized functions, there is a notion in which you have precise transform of that into constant.
Yeah, and that's kind of where I think the normalization term like breaks, like precisely at that point, because you can't divide by zero, but then you also can't like undivided divide by zero, but it seems like that's like really useful because precisely when you get to like reinforcement learning or like probabilistic models that you're trying to like actually like converge to a low standard deviation value because you want really high certainty, like a language model or something.
Mm-hmm.
Like I think that's probably where the stability that like as you start getting to that like towards Dirac, you need to have like perfect certainty to be able to say like this value is this value absolutely. But
Yeah.
computers we can't like really handle really, really infinitesimally small divides.
Yeah.
Or
So I think I think the reason why this works in computers with low precision floating point numbers, like effectively. Can you guys hear me?
yeah, yep. I was just getting some water.
Oh, sorry. So with effectively rather low floating point precision is that language is actually a very highly kind of constrained problem. So if you have this like very highly very high dimensional basis, it kind of necessarily has to capture the low rank structure of language if it's flexible enough, if it can be molded, enough. And why is kind of language necessarily low rank in when there's kind of like enough of it? This sort of has to do with I think just how big data matrices generally behave. That if you have lots of data, then you will find that it typically ends up being low rank because there's just no way for systems to exist in isolation. They always mix and they become entangled, and they exchange information with each other and so on and so forth. So there is always, if you have enough things to measure, you can always do some kind of dimensionality reduction really aggressively and derive a few low rank quantities, from that data that you would care about.
Although I would say that it's interesting about the model how you could define like extreme. You can define like just like thinking, right? Or not just thinking, but if you take like a distribution, you can force a model to be 100% certain in computers or even on a piece of paper, right? Because you could just say pick the mean every time, pick the mean. But you can't really represent that because there's no division by zero. So like, this is out there, but I wonder like why is dividing by zero in this case? Like it seems like being able to divide by zero would be a useful tool because you can literally like write a simulation that like this is what greedy evaluations are. So if you in supervised learning, this is like the primary way that models happen besides training with cross entropy to simulate it. But you can like most of the time when you're training like normal supervised learning models, for the same input you always get the same output like every time. For reinforcement learning, and unless you do like DDPM, or not DDPM, but the deterministic policy gradient methods, most of the time it has to be like it literally has to be a stochastic model because it's like the definition of like reinforce. It's actually like you need the log probabilities to even calculate the loss and backpropagate because your environment is not differentiable. But it's I think it's just interesting that you can literally have a perfect precision distribution, effectively a standard deviation of zero. But in math, you're not allowed to divide by zero. That's like here's the Dirac. Yeah.
So I also wanted to interject something actually real quick, that just because I think I finally understood Christoph's point, and I think it's a really interesting one, and let me know if I'm understanding this correctly, Christoph, but I think you're basically saying that when you parameterize things in terms of exponentials, it's convenient to define rapidly decaying functions, like, for example, the PDF of the normal distribution, and that's useful because these Schwartz spaces are spaces of rapidly decaying functions, or I guess in particular, they have rapidly decaying derivatives. And this class of functions happens to have kind of nice Fourier transforms in that the Fourier transforms are also in the Schwartz space. And it turns out that, well, so like the Fourier, why does the Fourier transform of the density function matter? Well, it's the characteristic function. And it turns out that when the characteristic function has derivatives, has up to k derivatives, for example, that means that all of the moments of the distribution up to order k are defined. And so there seems to be something useful about having rapidly decaying, about having density functions that have nice Fourier transforms, have smooth, well-behaved Fourier transforms, because then they behave nicely as distributions with well-defined moments. And so we want to have these rapidly decaying density functions, which we can get by using an exponential parameterization. Is that kind of the right idea?
Yeah, that's one angle you can look at it, and it's a brilliant explanation. Bravo, that you really nailed it. And yeah, and that sort of gives you this sort of composability that you really want. That you're always in the class of functions for which you can get this Fourier transform for them, no matter how you compose them from this class of rapidly decreasing functions.
I see. And like,
but hold on, just one second. But Fourier transform, I have no idea really how to describe it, other than to say that Fourier transform is essentially sort of like, how to put it. It's kind of like a rotation of a system, so that you're looking at it spread out over complex plane, something like that. I have this like a weird geometric picture in my head, And what this class of rapidly decreasing functions in this Schwartz class gives you is that you have basically a basis for representing spatiotemporal pixels, right? Because the Fourier transform is the time domain construct in this, and belongs in this class of Schwartz functions, and your representation function is also in the class of functions. So no matter how you're moving the system in phase space, treating time as a kind of a static geometric property, which is the view of general relativity effectively, then you're always within that space. Something like that. There's a real depth to this property. I've been thinking about it for, I don't know, like 12 years at least.
I see. And I think like maybe like kind of what you're getting at with composability is like operations that we do that take, let's say, as input like two different distributions and output another one. Like one thing that we often do is we add one random variable to another, and that means you take the kind of the convolution of two probability density functions. And another thing is like kind of conditioning one variable on another, and then you're kind of multiplying probability density functions together. And I think if I'm understanding correctly, you're saying like that this class of rapidly decaying functions is nice and is kind of closed under these ways of combining distributions together, in that when you take the convolution of two density functions or you like multiply them together, you still get a Schwartz function in the Schwartz class. Kind of, is that kind of the right idea?
Yeah, and I think yes, and I think related to something you might be way better familiar with than I ever will be, with the normal computing's sort of the first thermodynamic accelerator card, right? Like I don't remember too much the how it worked, but my impression was there was like a bunch of systems that effectively are sampling from a Gaussian using a physical process.
Right. Yeah.
Yeah. And I think in one presentation, Bev Jesus, described this approach as just a bunch of Gaussians, and extolled the Extropics, special kind of connected nanomachine system made out of Josephson junction as vastly superior. And it probably has interesting properties, but this business with rapidly decreasing functions and Gaussians, and why they just so happen to be so useful for everything, this smoothness property, right? Like that seems to suggest that it might be possible to have effectively this kind of Gaussian-based parameterization of the world. Just think about the success of Gaussian splats, how effective they are at representing volumetric data in time as well, right? Time evolution of volumetric data, and so it's really, really interesting that you have these like voxels of probability density modeled over time pretty much directly, So then you can think about like how you can do sensing as well. Like you can just sense this directly, right? You can have a bunch of sensors like this and capture a bunch of Gaussians, and a tremendous amount of possibility, because it just composes at all levels.
I see. Yeah, I mean, I think like, yeah, as you were saying, like we've so far really put forward ideas for like sampling from Gaussians. We have one or two ideas for non-Gaussians, but like it's there something on everyone's minds is like, yeah, what kinds of distributions can we actually sample from using like thermocomputing? And yeah, in my opinion, when people say like, oh, we're going to have a universal device that can sample from any distribution under the sun, that's kind of absurd. But at the same time, like we want to go beyond just Gaussians. And so it raises this question of like, how do we think about the family of distributions we'd like to be able to sample from? But yeah, I never actually thought about it in terms of this like Schwartz class of functions. So I appreciate you mentioning that, because I think that is an interesting idea of like saying, can we sample from distributions within some Schwartz space or things like that? I think is a cool way to think about it.
So let me put it this way. Sorry, just let me just let's say one very quick thing. Let me put it this way. This way you can essentially abstract it away so that you can have a system that's just simply good at Gaussian and compile whatever you want to sample, your distribution to it, right? So you can have a fixed array of essentially just a bunch of Gaussians array hooked up to sensors, for instance. And this idea suggests that you should be able to sort of compile whatever distribution you want to some operations that you can construct with these rapidly decreasing functions, right? Because Gaussians are rapidly decreasing functions with a rapidly decreasing derivative. So you can compile it, and if your array is precise enough, you will be able to represent it precisely. So that's a pretty big advantage, I think. Go ahead, sorry.
Yeah, sorry, go ahead, Yikes, yeah.
Sure, yeah. Well, and I think I'm fairly out of my depth here, but I guess I wanted to posit the idea. My my pet neural network has been the Kolmogorov-Arnold network for ages and ages. I haven't found anything useful really to do with it yet, but since we're on the topic of doing operating on an array of Gaussians and the types of computation that the two interesting things that I thought I would just mention and see if it sort of I don't know, kicks off anything is the ability to reduce a I am not remembering the term, but it's the ability to reduce a multivariate function down into a lot of univariate functions or equivalent univariate functions, and then the prospect of doing computation via splines rather than their normal configuration in the majority of other neural networks. I remember those two things being like the things that are kind of like grabbing me about it, but I'm not very good at math, so I don't really know exactly if that's relevant to the context here at all, but I thought I would just sort of like throw that out there and see if there might be some use for my favorite neural network in the context of like thermo rather than traditional computing.
So when you're talking about like reducing a multivariate function to like a bunch of univariate functions, do you mean kind of in terms of like separability of a function, in that you write it as like a product of functions of different variables, kind of?
So that's sort of the I have to like go back and look at the paper again, but basically like the interesting thing about doing a Kolmogorov-Arnold network is that I believe because normally you would use a multivariate function to do your training that is to some degree not separable, which sort of contributes to its inability to be interpretable. But if what you can do in the context of Kolmogorov-Arnold is decompose the multivariate down to a series of univariate Kolmogorov-Arnold proofs. So I'll see if I can grab the paper and kind of jog my memory a little bit. But I remember that being the kind of issues with it were that it's not particularly useful to do that in most cases with the kind of scale that we work with these days, just because like great, you can sort of decompose the function, but that doesn't necessarily do anything productive, because like at the end of the day you still need that function in order to perform the operation you're trying to perform. But considering that that we're kind of like getting into like sort of measuring these geometric properties and then using that for some degree of modeling we're doing here, if I'm following, which I'm probably not. But the that was sort of the advantage of being able, or that was the interesting thing about the CAN as opposed to the like other architectures of neural networks like RNNs and CNNs, etc. It's that they can use, rather than using the single multivariate function, they can reduce that down and then operate on each of the individual KA proofs, essentially.
Okay, cool. Yeah, I actually had. Yeah, I don't really know anything about cans, so I feel like we should try to like see if we can dig into like, yeah, what is this property of cans, and does it have like, if we wanted to do like a probabilistic can, right? Like if we wanted to like sample like the way that people do probabilistic Bayesian neural networks. If you want to sample from the posterior over the weights, like what if we wanted to do that with cans, and maybe this property you're talking about like has some interesting effects there. I think that would be a really cool thing to talk about. And especially if we can, maybe there's something in the book already that maybe it doesn't talk about it in the language of cans per se, but maybe it's somehow still relevant. That'll be a really cool thing to go into.
Yeah, the I did. It's been quite a while since I did that. I tried to do like a little presentation about cans a while back. But the kind of the three things that I remember is that about them is that we have uh, the the learnable activation functions can be on the edges. They can be on the weights themselves because they don't have linear weights. Um, every weight parameter is, I'm reading off the abstract here, every weight parameter is replaced by a univariate function that is parameterized as a spline. Which I know, like, I'm also out of my depth when it comes to like operating on these sort of like geometric concepts, but I know that like a spline and a Gaussian are both ways in which you can describe a thing that is in space. So it occurs to me that it may be more useful in this context if what we're doing is primarily like operating over distributions. Um, but I also, I've collected a whole bunch of people trying to do things like implement. I think one of the cool ones I found was like a fast Fourier transform in the context of a CAN architecture. Um, but yeah, it's sort of, yeah, it's like my pet architecture, and I really like to shove it into places. So I was hearing a lot of terms that are at least to some degree somewhat relevant to those, and it sort of like rung a bell. So I was like, ooh, maybe I'll just like throw that out there in the context of people smarter than me and see if anything happens. But it could be. I would be, yeah, it would be interesting to see if there's any kind of way to apply any of those sort of principles to some of the operations being described here.
I think the interpretability of cans is an interesting opportunity. Like if you can decompose, so if you have some like complicated multivariate function that you're trying to model, right? The question is whether it is decomposable into some smaller number of variables that are largely independent. And the answer for natural systems is yes. Typically, there's usually a low rank reduction of such function. And that has to do with the fact how natural systems work. When they interact with each other, they become kind of entangled with each other. And that starts to, over time, reduce their degrees of freedom. So when they're finally observed, they typically actually have few degrees of freedom left to them, even though they're embedded in this extremely high dimensional space. And that is why they, kind of can appear random to an external observer, but in reality, they're just like really simple systems that have very few things that they can actually do. So that's essentially what you're dealing with, and that's why it's possible to do that. And then the question is like, if you have the decomposition into these constituent variables, then they might be variables of interest. Like you may want to give them names. They're probably something that you're trying to measure for a reason. So this automatically could discover something like this from the empirical distribution.
Yeah. By the way, can you send that paper in our group chat? Because that sounds. I definitely want to read that. Awesome. Thanks.
Damn, I remember that paper now. It came out a while back. It's like that's actually a really interesting point that this happens. That you can basically that they move to Gaussians to get this kind of very good basis for representing this, and you have this measure of interpretability in Kant's because of how the basis functions are glued together, how you're doing that gluing.
We may have found the killer app. I mean, yeah, the jury may still be out, but I'm excited to see where this goes. Yeah, hear more about cans and probabilistic machine learning for sure. But yeah, also, there was something I wanted to ask you about, Christoph, too, that you mentioned before, which was kind of the idea of like compiling to multivariate Gaussians in a way, in that, like, in other words, you can sample from one distribution and then evaluate some function or do like post processing on the samples, and that effectively transforms it into another distribution. And what I understood you as saying was like, for a lot of the times, you can basically do you can sample from some multivariate normal distribution with some correlations, and then do some post processing to transform it into a sample from another distribution that isn't Gaussian, but still, in some sense, maybe preserves those correlations. And I guess the thing I'm wondering is like, that sounds like a good approach, and something we could do. Like, we could use that approach for hardware acceleration, for example, and say we're just going to make multivariate normal sampling really fast, and then do post processing to transform the samples into another distribution. But the thing that I'm curious about is like, when is the Gaussian sampling there actually the bottleneck? Because when it is the bottleneck, then this is like a really good thing to do, is like make really efficient multivariate normal sampling and then do digital post processing. But if it isn't the bottleneck, then you haven't really solved the problem. But that's just something I don't really know or have a very good understanding of. But I was just curious if you had any thoughts on that, Christoph.
I don't have a well thought out argument for this, but I have a feeling that you can sort of that in the future you can sort of like somehow treat it. How should I put it? Both backwards and forward for sampling and for sensing. That you have some kind of sensor, and that's usually modeled by Gaussian of some sort, right? Like where values are typically around a certain value, and they have typically normally distributed. Excuse me for a sec. Hey, normal distribution around that value, because it's a sum of independent events, and those events are effectively coming from a linear system, right? So they are independent because they're coming from a linear system. So it doesn't really have memory, because physics is a linear system, a linear time invariant system. So it's kind of like so then you're trying to shape essentially an extremely potentially high dimensional object like that, like if you're training a robot or something like this. So these tiny distributions that might be basically what kind of neurons, that's the basis, that's the resolution. Maybe at that scale, you can get to that scale, and what you're routing to that neuron, you don't even have to process that much. You're just, for instance, routing raw pixels from the camera. You can train a generative model this way, basically from pixels to hardware directly to just simply predict the next pixel, and then do a sparse autoencoder or a linear probe on top to do classification, for instance, to use it for downstream tasks. So basically, this starts to look like a cybernetic brain at this level. So that might be the scale where you really see the improvement, when we're just ghost in the shelling ourselves to a prosthetic.
I see. Okay, cool. Gotcha. Yeah, I guess one thing I kind of thought of as you were saying that is that, like, I guess whenever if we can take samples from a multivariate normal distribution and then transform it into another one by doing a kind of component-wise operation where we just apply the same function to each component of a vector, like an activation function kind of, then it feels like in such cases the Gaussian sampling, we might expect it to be the bottleneck, because we have kind of order of n squared pairwise correlations, and then we only have to do like order of n, like kind of component-wise operations or something like that. But
Yes.
Yeah.
Yes, but just one second. Sorry, like I just have to say this. Like what you just described, I think it's exactly what was described in this paper. Deep physical networks trained with backpropagation. So they have a bunch of random physical systems, like a speaker and microphone, or a crystal and a camera and a laser, or RCI circuit, and they just simply blast the signal through them and use them as non-linearities. And they show how you can actually train a neural network composed out of these systems to effectively do your computation. So you can compute with any arbitrary physical system at all with zero effort. But if you can model the system.
I mean, I don't know what
Yeah,
zero effort, but all right.
But, hold on. Let me explain what I mean by that. Like, you don't have to model that physical system, because that's in general, we don't have a way to do that. All you have to do is to train a kind of a digital twin neural network that predicts outputs of that system from inputs, and you can use that neural network to basically as a gradient estimator for your gradient descent. So now you would have like lots of accelerators that are produced with some variability in the process, just to give you slightly different distributions. You really want that noise.
Okay, yeah. It's funny because when you were describing it, I was thinking to myself, that reminds me of what Peter McMahon and Logan Wright do. And then I pulled out the paper, and it's written by Logan Wright and Peter McMahon. So this is a really cool line of research of like, it's not exactly a digital twin, but like training digital like simulation of the system, I guess, to get a desired like input output relation, and then using
exactly
your system, which has some interesting nonlinear dynamics, to and instead of weights, like having trainable weights, they think of it as like having two kind of inputs, where one of the inputs represents the weights and the other represents the actual inputs of the problem or something, I think. But, yeah.
Exactly. And you know, like with a laser and a crystal, there's like a lot of interesting possibility for optical. That's the paper. Like that's one of the best papers I have ever read. I mean, it's a masterpiece.
Cool. Yeah. Actually, and I'm not sure if people have thought about using this stuff for actual probabilistic machine learning yet. So that'd be a cool connection to make too. Like maybe if like using these physical neural networks, which just to keep them distinct, there's another thing people call physics inspired neural networks, very different thing. But these are actual physical neural networks. We're actually using some physical system that has some nonlinear dynamics to evaluate a function that you can have learnable parameters that go in there somehow. But yeah, using these for probabilistic machine learning, I think that it hasn't been thought about in that way yet. So that's something I'm pretty interested to think about more.
Yeah, I wonder if that's why they use splines. I guess, Yikes, you mentioned the thing about like decomposing a Gaussian distribution into, or like like some function into like many composites of that function. I wonder if the reason they did that was kind of almost to be an activation function, because if you have a spline,
it specifically is, I believe. The idea being, so the learnable activation function, we want to, rather than using one large multivariate, we want to decompose that down into like the Ka proofs, and then we want to train those proofs rather than weights at all. So every weight parameter being replaced by a univariate function, which is parameterized then by a spline. The main issue is with like applying that to modern architectures is that it's generally not really that much more productive to do that in a lot of cases, and like you have to deal with all the weirdness of like, okay, now I have a bunch of like splines that I have to deal with, and my math is all wiggly.
That's crazy, because if you parameterize a spline, you're essentially giving the parameters the ability to reshape itself, right? Like if you pass in to like a Gaussian, you have that same, you can do the same kind of thing, right? You can like control the shape of the Gaussian with the parameters. But when you have a spline, it's like, yeah, like you're not just like having some value be the function of another value in the sense that like of an activation function, but you're like literally giving it the ability to tweak its own like activation, so to speak, which is really interesting. I can see that getting really unstable.
Yeah, that was so. Yeah, in the paper, that was largely what they ran into as well. Or I think basically it was mostly a proof of concept because they really could only apply it to toy problems because of that sort of like kind of instability sort of issue. But when it does work, it's pretty cool. But it's just like it's real like it starts getting real iffy once you start trying to scale it up and do something even something as like small as like mnist as an actual problem. Yeah, it was kind of the issue.
So that's why you need this. That's why you need to be this especially careful about smoothness, because if you want to go deep into that kind of information processing system, you need to very precisely propagate information through these signals, right?
Although,
so that's why. Yeah.
I'm wondering if in order to manage the smoothness, can you like if you could measure the entropy while you and then like normalize it, like soft masks your entropy values or something weird like that. I don't know. That's kind of where my head is like, okay, the problem is these splines are too wiggly. So if we de-wigglify the entire plane on which they're operating, then they will not be wiggly because they can't, kind of thing.
Yeah, really creative. I think by having a learned activation function, you can kind of simulate this by having multiple layers like in your network. Like the traditional way to address, nonlinearity for your data set, like trying to model, is like activation functions. And obviously if you have more depth, you can kind of like, it's arguable if you can make more nonlinearity, but for the sake of like multipliers, you kind of can. But like stacking more layers of like a sigmoid or something, it kind of allows you to tweak the shape of the activation function, so to speak. Like you're not really tweaking the activation function's shape like you would if you were using a spline, but you kind of are mutating the space more and more and more in a nonlinear way when you have multiple stacks of these nonlinearities. So it seems like another way to solve that problem, for sure. Might be more smooth. That might be why we kind of like use stacked layers with activation functions, just because they're like, you have one static, usually like one activation function, like a sigmoid or something, but applying it multiple times with different transformation matrices, like you can bend the space more and more, while not like having like being able to like you were saying, like have to worry too much about the curvature of that spline getting like infinitesimally weird, like around some point or something, like tangled.
Yeah, I think the sort of bombastic claim is the cans can beat the curse of dimensionality when there is a compositional structure in data, achieving better scaling laws than MLPs. But the problem is like getting to those conditions is really difficult, and keeping it in those conditions as well as you scale up is also kind of an issue.
That's where I think this rapidly decreasing functions business might actually help. And the reason why these functions show up, so often in modeling natural systems is because physics is a linear time invariant system, right? Like the universe as a whole is some kind of computational construct that is evolving according to rules that can be nonlinear. But physics, as we practice it, is essentially looking at the linear time invariant aspect of it, meaning that physics is the same in the morning and in the evening, and we always practice physics linearly. We basically say that we need to find a way of untangling the system to such a degree that at some point I will have effectively a linear variable, because if I can control something linearly, then I really kind of understand the system. I basically untangled all of its degrees of freedom. It no longer exists as something separate, from me. I can predict it exactly. So to the degree to which you linearize a system is the degree, to which you get control over that system. effectively. So you have to. So there's something inherent in reality, and that's inherited from geometry of information processing. It's essentially, this is where a general relativity actually kicks in, and sort of like, you know, the structure of the energy structure of causal systems, because general relativity is really about point events and causal relationships between them evolving. It's a very computational model. If you think about it, for instance, the way Sir Arthur Eddington talked about it. So if you find the right quantization, these voxels of what do I call it even? You know, these sort of like voxels that give you spatial-temporal sampling. So you can, those would be your little Gaussians. If you can somehow make that work, then you would have effectively like this perfect coupling to, you know, between sensors and their processors. You could calculate capacity of it. There would be a lot of things you could do with that kind of model. It would be like a Turing machine for you know, composing probability distributions to achieve something.
So one thing I wanted to kind of add in here was, as I kind of understand CANs, well, I guess just in general with neural networks, you have kind of these alternating like linear mixing and then nonlinear operations, and we have a lot of parameters, and usually all of the parameters basically go into these linear mixing operations, and very few, if any, of the parameters go into learning the nonlinearities. And in CANs, instead, you start using a number of parameters to specify the nonlinearities, and you're going to need some number of parameters to specify these splines. But the hope, I guess, is that maybe the total number of parameters you need, including both like the linear mixing and the new ones you have to specify the splines or the nonlinearities, doesn't scale as badly using this approach. And so I kind of understand it as saying, like, let's spend more effort on learning the nonlinearities than learning the linear mixing part of our model, if that's right. But yeah, curious to hear how other people interpret that.
Yeah, it seems like choosing the method for optimization is a lot about the dynamics of the data, like how it's kind of going around like your neurons, I guess. Like if like that, I think I saw one of the figures that had been shared in the book. I think it was like the chapter 24 figure, and there was like a swirl data set. I could imagine that the actual shape, like the literal physical shape, whether it's in 2D like a swirl, or if it's in some n-dimensional space, some crazy like moving particle something, like I would imagine that using, you know, different types of optimization methods, like for example if it's like splines mixed up or like something, or stacked layers, or you've got something else, maybe like an attention network or something, like all of these like architectures and methods for actually like trying to make sense of the data, like probably plays a crucial role in the actual like quality of that network.
I see. So basically, like your point is kind of, we shouldn't really hope for any one architecture to have a better scaling laws than other architectures in general, because the scaling laws are going to depend on the interaction between the architecture and the data set, basically.
Yeah, I wouldn't say that it's a perilous task for that search. I would say that, yeah, that they probably have different scaling behaviors for sure.
Right. Yeah, that's an interesting point. Yeah. Because like people often think about it as like, oh yeah, can we find like this new like silver bullet architecture to get rid of our problems with scaling laws? But yeah, I think that's a good point, that, you know, it's really going to depend on the compatibility of the architecture with the data set or something. Not to say that there may be some improvements, unambiguous improvements that can be made. Like maybe, you know, there is an architecture that's just unambiguously better than another one for any data set. But still, in general, you know, there will be kind of pairings of, you know, one architecture is better for one kind of data and another. And I think we don't necessarily have the language yet to describe like what is it about one data set that makes it better, better suited to one architecture or
Yeah.
whatever.
Yeah, for sure. Like if you were to have just as an example, like if you were to take an activation function that sets every value to 0, like of course that function, like whatever you compose this model like of however many layers, like you're always going to have like a 0 output. So it makes like there's obviously certain models that will necessarily be better. Like if you were to just use a ReLU instead of that. Yeah. Um, yeah, it's interesting.
Right. Yeah.
But so effectively, to summarize what you guys just said in a slightly different way, I propose to state it this way, that it really depends on the geometry of the problem. There's a sort of data set architecture fit has to do with the sort of like intrinsic geometry or structure of the problem, and the sort of hypothesis is, right, like that beyond certain fairly minimal level, all computational systems are effectively equivalent. So it's just a question of tuning the hyperparameters the right way, and you should be able to, in principle, get pretty much any kind of architecture, within the same fairly reasonable range. And CNNs, and visual transformers, for instance, are still kind of like on par in terms of in terms of performance they achieve, although they model very different kinds of things. So you get something for the architecture of a transformer gives you a very, very different and a much more powerful distribution than when you get out of CNN for the simple sort of recognition pattern matching tasks, right? So we are acquiring a language of these trade-offs. What exactly you're extracting, and what can you do with the distribution that you actually acquired.
Well, so what you were just saying, Christoph, made me think about something, which was like if we wanted to have like a kind of almost like a kind of Church-Turing hypothesis for neural networks, like what might that look like, right? Because Church-Turing or Church-Turing thesis, right? It's like a very powerful thing for digital computers because it basically says like, all of these different models of computation are equivalent. And if a problem, it's really the property of the problem that matter, not the property of the computer. If a problem is polynomial, it'll be polynomial on anything that's a Turing machine. You can't create a Turing machine that's super polynomial for a polynomial problem. And it made me wonder, like, could there be some similar result that we don't know yet for neural networks, where it's like it's really a property of the problem that any architecture within some reasonable restriction will have the same scaling law. But obviously something I certainly have no idea of at the present, but definitely curious if anyone has thoughts on that.
I think it's a more general it's a kind of a more general structure than just related to neurons. And I think essentially, how should I put it? The reason this works is effectively why it's possible to connect quantum and general relativity. I have this crazy, weird geometric structure in my head that I'm having difficulty to describe, but I can see the way for unification. Basically, what it says is that if you have a system that has non-local correlations, you will still be able to describe it geometrically using a family of sufficiently, smooth and expressive functions. And the reason for that is that the reason why you have general relativity, why Einstein's equations are geometric the way they are, is basically because that's the shape of causality. When you have causality, you automatically get geometry. And Einstein just kind of like, he put a blanket over space and noticed that it's the blanket is a bit bent, and found a way to fit this sort of sensing fitting mechanism, which is the metric tensor, right? It's a kind of like metric tensor is like a patch of a neural network effectively. it tells you how you need to curve space in the local patch so that everything that happens in the patch looks linear to you. That's the transformation from your subjective coordinate system as an observer to accelerated, non-accelerated coordinate system. So general relativity is an observer-centric theory, and so is quantum theory, but they are in orthogonal spaces. One of them is geometry, like this sort of I think this is the same thing as ADS CFT correspondence. This holography, like
Well, wait a minute. Sorry, you kind of lost me there a little bit on it. Like, could you just kind of distill down the point about the
sorry
general relativity and the metric tensor, and like, yeah, how does this relate to neural networks, etc.?
So basically, the thesis is that this geometric there's a really good reason why these geometric functions are like EBMs, why they are so good at modeling these distributions, and that's because it's kind of like the natural structure. Sorry, I got tangled a little bit.
Okay, yeah, no worries. I mean, it's certainly a complicated.
Okay, I really would like to explain quantum and general relativity, right? You want to explain how these things kind of couple together. So quantum theory, you can look at it as essentially saying that like I can measure something about the system and I have a limited interface of how I can measure. What can I say about that system? And quantum theory discovers that there is such a thing as non-local correlation, that I may be able to measure all the observables there are that intersect with me and that system, and I won't be able to essentially linearize that system, that it has more degrees of freedom that I can model, or it so happens that also it's actually that it simply needs to be a sufficiently sophisticated computational system that I won't be able to I won't be able to predict it exactly. So that's the kind of quantum mechanics view. And orthogonal to that, in some sense, is the geometric view, where effectively causality is what creates geometry, and you have like some kind of movement, a slight change in phase space. So the system evolves, and you can say like, well, I'm going to scale it so that I can see it evolving according to this linear rule, and that is computation. Or when you iterate that, you can get arbitrary curvature, right, by basically adjusting the step size and sort of just iterating on the system however you want. So you can compute curvature more or less precisely. So this is how you can connect quantum theory and general relativity. There is a kind of like a kind of a rotation. And essentially what I'm saying that this geometric object that is given rise to can always be characterized using smooth functions, like especially these smooth, rapidly decreasing functions, or something like that. That would be the thesis, that the fabric of reality has this geometry to it on one end, and has this discrete computational nature on the other hand, and there is a smooth transformation between the two. It's a manifold, effectively, if I'm not mistaken. That's the meaning of the word manifold.
Okay, gotcha. Yeah, I feel like we almost need to have we should maybe even have another kind of space to talk about these like kind of grand unification ideas and stuff like that. I think the thing I'm still not totally following is that like you talked about like non-local correlations and relating to quantum mechanics, and of course it's true that like non-local correlations are something that are studied intensely in quantum mechanics, but it's not just non-local correlations, which are actually also a totally classical, also totally exist in the classical world, but it's really non-local or just correlations in general that don't satisfy the Bell inequalities. So I guess I'm wondering, like, is there something important about the Bell inequalities and what you're saying, but I also I think I need to just understand better at some point like this connection between like quantum mechanics and metric tensors and machine learning. But I think there's something there to understand better for sure. But yeah.
Yeah, that's sort of related. It's a fiendishly complicated story. Like I can only tell it with enough resolution. But basically, my research program, so to speak, is essentially based on three pillars. One of them is general relativity. The other one is Friston's active inference and free energy principle. And the third one is, a computational approach like Wolfram's model and his work on observers. And if you look at the nature of observers from these three perspectives, sort of simultaneously, and say like, well, how are they similar and how are they different? What can I do with each of these models of what's happening to the universe, and what are their limitations? What is it that they cannot tell me? So you sort of characterize the space between them. Then you will find that there is a continuous deformation from Wolfram's system of hypergraph evolution at the sort of like this lowest resolution of space, atoms of space. You can continuously deform it all the way to general relativity, and in the limit you get precisely the equations of general relativity. Or you can go back to Wolfram's model and you can continuously deform it into effectively getting the Schrodinger equation if you deform it in a different direction. So that's the limiting case. And the reason that works is that computation is universal. So that's the Church, Turing, Gödel, and I don't know who to attribute the rest of this thesis. I suppose I'm going to be bold and going to call it, mine.
I see. Okay, so you were kind of getting at like the Wolfram's like grand unification stuff, where he talks about like quantum mechanics and general relativity coming down to this like Reulead thing. Now, I will say that there's definitely quite a bit there's quite a bit of skepticism about his ideas among physicists at least, but not to say that he may end up being completely right in the end. But yeah, it seems to be maybe yet another kind of model that has enough flexibility to describe a lot of things, similar to string theory, but not necessarily there's any like definitive evidence yet that it's the the right one to use. But I think it's very cool thing to talk about. But it was go ahead, Christoph.
I just have to say, like, Wolfram's model is something else entirely. It's unquestionably correct. It's correct by construction. All theories of everything, if they want to encompass everything, they have to be constructed to do that. And at every step, you can simply ask the question.
Okay, so when you say it's correct by construction, like, so he sets up a theory with certain rules, and you can say if you follow those rules, you'll get the prediction of his theory correctly. But the thing that's not obviously correct by construction, not obviously correct to me, is the idea that the universe is built out of graph rewriting rules on hypergraphs, because that's what he posits, right? He says that really at the basic level, you have these hypergraphs and you have graph rewriting rules, and that explains kind of how things propagate in the universe, and that really we should think about kind of our ontology as at the most basic level as being these hypergraphs. And that's the thing that there's no reason to me that that's the way we should see the universe, I guess. But anyway, not to go too deep into these that's almost a metaphysical question rather than physics, or even more distantly related machine learning, or still far probabilistic machine learning, I guess. But maybe there's a way to tie it back. I guess. Well, I'm still curious about the angle of like whether there's some interesting way to think about probabilistic machine learning with cans. Actually, I mean, I think the one thing that's always fun to do is to take some kind of architecture, some neural network architecture, to say like, okay, what's the function that you get out for your predictions, and then including some loss function. What function would you get? What distribution would you get if you just took kind of the Bayesian posterior for this neural network? So it's definitely something I'm interested in. If there's some interesting functional forms that pop out when we apply that to cans, and maybe there's even some deeper connections to these different kind of fields in physics. But yeah,
I'm not sure I've heard of cans. Well, Oh, gotcha. Kolmogorov of what? K-A-N? Yeah, yeah. Kolmogorov. Kolmogorov. Kolmogorov and Arnold Network. Gotcha. Gotcha. So this is where they have like splines as the neurons. Is that the figure interpreting? So is Kolmogorov's interpretation disjoint from uh you said the universal function approximation theorem, right? Or is it like how is it disjointed from that? I guess. Got- I see. So Kolmogorov complexity, that's like the measure of compressibility for like some sort of
So can I jump in? So essentially, by using splines, I think they enforce compositionality in such a way that you can do the decomposition later. Whereas, like if you're composing outputs of nonlinear functions, then you can't quite necessarily, I think, enforce it this way. That you will always be able to glue them very nicely, right? I think this is the difference in how the universal approximation is applied. Because universal approximation simply says that you can, with a big enough MLP, you can get just any kind of smooth function or something like that, just like to any degree of accuracy with enough neurons. So you can just keep ramping up precision.
So are they assuming independence of those variables, or are they assuming there's like covariance between? I'm assuming you have to have covariance between the composite functions, right, and like the target function. Yeah, I like the visualizations.
I see. I was just diving down a Wikipedia rabbit hole, and it turns out there's this interesting connection, I guess, between Kolmogorov-Arnold networks and Hilbert, one of Hilbert's problems, or Hilbert's 13th problem. But I'm still trying to fully understand this. But yeah, so I guess this Kolmogorov-Arnold representation theorem kind of says that a function of n variables can be written as a sum, as like a sum over sums of where the inner sum is over functions of the individual variables, and the outer sum is functions of those sums. And it's kind of saying that like you can build any nonlinear function where the only mixing you do between the arguments is sums, and then the nonlinearities only get applied on like a component-wise basis, I guess. But yeah, I'm not totally sure how this relates to the 13th problem, but it seems interesting. Oh, okay. I think I kind of see. Like, in other words, like you need a lot more depth in low dimensions. You need a much deeper network to get the same accuracy as you would with the Kolmogorov-Arnold network, that can just kind of fit these univariate functions much more easily, I guess.
That would make sense. Yeah, I think this would be like a replacement for depth in the network if I had to like just use pure intuition.
Right. Gotcha.
Hmm. Pretty interesting stuff. You brought up the idea of like having nonlinearities between the functions and have the functions themselves be like totally linear. Um, like, can you elaborate on that?
Right. Well, I mean, kind of what I was thinking is that like, I mean, right. So in MLP, for example, when we run inference, there are things that there is kind of non-linearities, and then there is linear mixing between the different components of the input. And when I say components, I just mean, yeah, the different elements of a vector. And typically, like the mixing, or how does one component of a vector talk to another, is through these linear transformations, matrix multiplications. And then the non-linearities always happen component wise, or in other words, you just apply one, you have a nonlinear function that has one input and one output. One number is an input, one number is an output, and you apply that same function to each component, right? Your activation. And it seems like this Kolmogorov-Arnold representation theorem is even going a step further, in that the mixing operations don't even really need to be. They can be even kind of a smaller class of functions than like general linear transformations, but can actually just be adding the different components together. And the only difference between that and linear transformations is that you aren't multiplying them by any kind of coefficients before adding them together, I guess. So I guess it just like kind of takes it puts even more of the burden on the like nonlinear component wise operations, and the mixing operation becomes even a little bit simpler, as I understand it.
It sounds like residuals almost. Um, you know, there's some interesting, uh, yeah, like when you apply the residual, and I think you maybe brought the like NLP in for like through time, like if you're like trying to communicate with the next layer, like you would infer like a token and then pass that back through the model for the next prediction of the token. Like you're kind of like you're almost like leaving a full prediction for like the next cycle, kind of. Uh, yeah, okay. The yeah, I can imagine like this having an impact on the way that a language model would express itself. Like if you were to predict a token that is like really rare in this case, because if you're doing inference, like you can obviously choose like how what temperature you want those outputs to be, and if it's a higher temperature, you're giving more randomness to the network, right? So it's like more likely to select more random tokens while it's like you know inferring. Um, it would be really interesting to see a model that can like adapt to its own. They probably do in some respects because it's like that next token is being brought in to the next prediction. But when you do that, you're only really telling the model like, hey, like here's the next word that is adding to your context, as opposed to saying like, hey, here was the token, but also we were like really uncertain about it. So like, maybe it would be really interesting to speak with a language model that has this adaptation, like, and actually uses it, like, where it's like, like I would say like this sentence, but I wasn't really sure about these 3 or 4 words, and so therefore it like kind of like, but like I don't know. Yeah, in reinforcement learning, it's I think it's interesting. It kind of like from a higher level when training like supervised learning versus reinforcement learning models, it's a little bit harder to gauge what's going on in reinforcement learning models. I think primarily because um, the entropy term, like, and this is actually probably, now that I think about it, pretty much any probabilistic model that you would train, like maybe even language models, but. Um, like as you're training and your model becomes more and more and more and more certain, it's not actually a a great measure for what the performance is. In a way, it kind of signals like, oh, this model converged more on a specific set of like priors, um, but it doesn't necessarily say like that it found the best answer, like, or the most, like the lowest loss in your function that you're trying to optimize. Because Yeah, like basically you could have a model that is really certain about certain tokens for NLP, for example, but it could be just predicting like yeah. Yeah, so I wonder how the influence of these kinds of models that are able to like adapt with their certainty levels known to themselves as like I wonder how that would affect in other ways.
As you so it's the idea here that if you have like token by token entropy estimates, then you can use those to trigger kind of like control flow operations instead of just producing more tokens, basically. Gotcha. That's cool. Yeah, that sounds interesting. Who's working on that specifically? Actually. Okay. I see. Gotcha. Yeah, yeah. That sounds pretty. Because I've heard this term, yeah, like entropy sampling and stuff. Didn't really know what it was, but yeah, I think that kind of clarified it. That you're yeah taking like you're getting the entropy of each token and I guess var entropy. That's like the like variance of the entropy or something. Gotcha. And by the thing that by that, like the thing that one run has that the others don't, it's basically that you have many tokens that have similar confidences, and then suddenly the confidence increases at the end. Is that right? I found this paper. Is it? I found a paper called "Chain of Thought: Reasoning Without Prompting." When I searched that, okay, that's the one. Okay, yeah, yeah, I'll read that. Also, let me send that in our group chat too, because this does sound like something on kind of on the probml side for sure. But oh, cool. Yeah, 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 yeah. I'll check out the Discord. It would be cool to yeah to see if we can yeah do some community building around that for sure. Right. Yeah, I also think that, like, yeah, the ideas you were talking about is really kind of fun stuff to think about too, because it's like this question is like, yeah, if you have a bunch of tokens that are low confidence and then you have one that's high confidence, it's something that's fun to think about intuitively, right? It's like if I'm not very sure about like, I'm writing my notes, I'm doing my calculation, I feel uncertain, and then I'm like, okay, this is the answer. Underline it, put a box around it. Is that an indicator of like a good kind of chain of thought? I think is a good is a very interesting thing to think about. Yeah. Right. And what's GSMAK? Oh, gotcha. Okay, found it. Yeah, I see. Okay, so basically the benchmarks are kind of end to end. Like, does it get the answer right in the end? Basically. I see. So the questions about generalization are less about the type of problem maybe, but more about like how the answer is actually formatted. Oh, I think I see what you're saying. And like in other words, like if it's a problem like where it's like just an arithmetic problem, for example, where the answer is just a number, there's really like only one way to kind of answer it correctly. But there could also be problems where like you could phrase your answer very differently or use completely different words and still answer it correctly. Well, actually that reminds me of something I was reading about like estimates of entropy of the output of an LLM that take into the account kind of like synonyms. Because if you have two answers, like let's say you have two answers that each of them you give with like 50% confidence, but those answers actually mean the same thing, then you really only have one answer that you're giving with like 100% confidence, and that needs to be somehow taken into account. And so, yeah, I think there was some scheme they had where they like used another pass of an LLM to like tell whether answers meant the same thing, and then like kind of aggregate synonyms. But, yeah. Right. But well, I also think like it might make sense to do the synonym kind of detection or similarity search before entropy is ever calculated. Basically, just because like entropy, you know, in order to really properly determine this how uncertain it is about its output, you need to know whether it's uncertain just because it's not sure how it should phrase its output, or because it's really uncertain of what the answer is. And in detecting a delta a change in the entropy, you should be, I would think, be more interested in whether it changes its uncertainty of fundamentally what the correct answer is. Whereas if it's changing its uncertainty about how the answer would be worded, that may not be more important. So I would maybe imagine a system where before entropy is ever computed, you do this similarity search and kind of synonym aggregation. Then that goes into entropy computation, which then goes into detecting deltas or changes or something.
Yeah, and if you pass those back in as tokens, you can measure like the certainty levels for each token, and then maybe somehow even correlate like the the speed at which you're changing those, like if those samplings of tokens are changing like as a compounding error, like, okay, I'm making more and more certainty or more less and less certainty, maybe the model can look and say like, oh, I'm more likely to make. Yeah. Mm, interesting. Yeah, you get like really abstract thought there. Whoa.
Well, that's kind of cool. I mean, you could even do a simple, like you could do a pretty simple experiment where you just do chain of thought prompting, but in each prompt you also include like the highest kind of logits for the previous tokens or whatever, and then and so you just tell it like what were the other outputs you considered, and see if that improves performance on these kind of end-to-end benchmarks would be interesting. Right.
Yeah. Yeah, like giving as many of the training variables as you possibly can to the agent itself and seeing, like, it's almost like another perspective of meta learning. Yeah, have you ever asked like an LLM like what the experience of training was? Yeah. Yeah, okay. I like that. I wonder if you could I wonder if you could, for a model that's more aware of its training, I wonder what it would say if you could be like, "Oh, what," like if it's able to like recall all of those like distributions that it observed in the past, um during this like journey through like really high loss to really low loss. um I wonder I wonder what it would say about these machinations.
No, I
No.
haven't seen that.
Are any of you familiar with uh, the iterative decoding of modern error correction codes?
Like Hamming codes?
So Hamming is more of a classical kind of encoding technique. Modern codes, you have like turbo codes, and you have low density parity check codes. There are some fountain codes, things like that. But essentially, what these new algorithms do is they have sort of it's an iterative belief update algorithm, roughly speaking, where you receive bits that have noise. You assign basically a log likelihood, sometimes a log likelihood ratio, because you have a 0 and 1 most of the time. Some you can use um, other fields, but usually the binary field is the one you're working with. But you assign basically log likelihoods, and the code itself is basically a set of constraints through which you can essentially propagate these beliefs and get essentially an updated state of beliefs on the bits, right? So it's sort of you're doing well, you're doing probabilistic inference, but um, it's I sort of think of it as doing reasoning on noisy observations, sort of denoising according to essentially a world model, where in this case the world model is, this artificially constructed set of constraints between your bits. But I saw that the topic was probabilistic machine learning. This is actually something you can do in models where you might have a hidden belief state.
Wait,
And you
wait.
actually
Actually,
have
I
an
just want
iterative
to.
algorithm where you.
Sorry, real quick. I just wanted to, understand, Andrew, what you were saying. So you were talking about, error correction, and as I kind of understand it, a lot of error correcting codes, they work by saying, you have some set of code words. If what you get, your signal out is not a code word, something went wrong, right? Some
Right.
error occurred, and you basically find the closest code word in some
Yeah,
distance.
that's the decoding
Okay.
operation, right?
And I think you're kind of saying, well, there's also this other class of error correcting codes where instead of just saying what's the closest code word, I have some process of like iteratively approaching a code word by transforming the thing I actually received. Okay, that's very interesting.
Generally finding the nearest code word is the decoding operation. The trick really in information theory is how do you do that in a way that's computationally efficient. And these sort of iterative methods have turned out to be essentially magic. In a sense, they're like you can get capacity achieving codes this way, and you can imagine doing this with like next token prediction, where imagine you have a prompt, right? And that's basically a sequence of you can think of bits in error correction code as the tokens, right? You might receive some bits and the rest are erased, in which case like the ones that you receive are essentially the prompt, right? And then so in the language case you might receive like the start, and then you do sort of an iterative decoding procedure to gradually not like all in one, right? Usually we just run the model once and we get out some logits, and then we sample the next token from that or whatever. But you can imagine just taking the soft outputs, maybe even just running them through again in a language model that is able to take not just input tokens, but also is able to take in like soft beliefs on input tokens and then iterating on that in a way.
I see. So I think like you're kind of saying there's still a way you can still conceptualize the problem as still finding the closest code word, but just like the method of solution is different in that you're doing it in this iterative way, and maybe you could be doing it like you could do it using a language model. So I guess the question to me that comes up is like, how do you train? Like, how would you sorry, how would you train or like fine tune this model to like be better at like error correcting code or stuff like that? Like, is there a framework for that?
Oh yeah, I actually don't think making an error correction code is interesting. I think there has been work on using neural networks for the error correction problem, like for actual error, like bit decoding on a noisy channel. I think what would be interesting is, given that these iterative methods have literally been magic for the error correction problem, I kind of wonder if they could potentially be magic for the language generation problem as well. In some sense, the iteration is a reasoning process on a probability distribution where maybe instead of taking a probability distribution on code words, we're actually just iterating on the probability distribution of real world knowledge.
Okay, I see. So what you're saying is less like applying large language models to error correcting codes, but more like, is there a way to apply this new theory of iterative error correction to language models?
Yeah,
I see. Well, I was wondering, like, because this is something I'm not familiar with at all. Like, if there's like a very like a simple example, like kind of the simplest possible example of like one of these iterative error correcting codes that you could take us through or something like that, or even just like higher level thoughts about how they work, I think that would be really, really relevant.
let me think. So there is an excellent book that you can find a PDF of called I think it's Modern Coding Theory. It actually is quite good at explaining some of this. Modern. Yeah, that's the one. And it should be fairly easy to find a full PDF of it.
Okay, gotcha. I think I found it. Yeah, modern coding theory. Awesome. Thanks. Okay. Yeah, I'll take a look at that. Nice.
Yeah. So a lot of this comes from, I would say a lot of the magic comes from just not using hard decisions, right? Like you run an LLM, usually you have to hard choose your next token um, to move forward, right? Now you can do a bunch of sequences to sort of sample the space of possible futures, right, and select among them. But it's still kind of restricted in that sense. But if we could just directly work on the space of of like basically the uncertainty space, right? Um,
Hmm.
there could be gains in inference from that. I have a tiny baby LLM. I don't have any GPUs right now, but I'm thinking about buying like building a multi 4090 system for my personal use and trying some things out. But I'm gradually working towards trying some of these ideas.
Hmm. Yeah, I mean, I'm pretty intrigued by this. I think like yeah, sometimes these kind of higher level like breakthrough connections come through. Like for example, I think a lot of people realized at some point that there's a very deep connection between the idea of like compression and decompression versus
Hmm.
like generative models,
Yeah.
which is I guess namely kind of that if you have a generative model, you also have a compression algorithm in that your whatever kind of you can I guess you can kind of think of the distribution that you're trying to sample from the end as being very compressed by your
Hmm.
generative model, and it
Yeah.
starts from
Yeah.
almost something random and maps it into uh and I think that there also may be like an interesting connection here with like kind of encoding and decoding, error correcting code theory, maybe. And so I guess the question I would ask is like, let's say that it did happen to work out that by using these iterative error correcting codes and applying those to generating new tokens and language models, we got much better metrics on question answering or something like that. Would that like imply something about kind of the nature of the task or of the model or something like that, or any thoughts on that in general?
Um, I'm not sure if this is a thought specifically on that, but I kind of feel like next token prediction will have to be uh, replaced by something else. Maybe something similar, and maybe we're kind of going in that direction already. I feel like when you're predicting, like these models are trained to model the distribution of language, right? But within that distribution uh, is basically wrong stuff, right? And maybe we actually don't. Maybe like getting that distribution itself is not what we want, but maybe we want something more like denoising, right? And in that sense, uh, maybe what we're doing is like the training data, say, is an observation, a noisy observation of some underlying structure. And it's that underlying structure that we want to model, not the whole distribution itself. And then when we're doing inference, we actually want to constrain ourselves to that underlying truth structure. I don't know if I'm making sense.
Well, I did think that the point you made about like, yeah, matching the distribution of natural language that is out there in the world is a very different problem than like producing true answers to
Yeah, right.
questions that appear in the world. But I wasn't sure, like, were you talking about like an approach to like kind of get around that problem, or yeah, how are you thinking about that?
Um, yeah. Yeah. Like in some sense, we need to do like a nearest projection onto the underlying manifold that is actual truth instead of like the space of like the probability space of observations.
And it's too bad that Christoph left. Is Christoph still here? Because he would love that. I know he's a big Rulliad guy. So no, that's interesting though, actually. But well, so okay, so on that topic though, right? Of like, can we? How do we build models that get to the yeah, right, the underlying truth? Um, can we model? Can we modify the model so that it tracks with the problem we addressed or that we want to address?
Mhm. I do
And
think we have some sort of forcing function towards that, which is like the later like RLHF type things, you know. Um, I think those kind of maybe in a roundabout way are a forcing function towards underlying truth. But if we could do it like more directly.
actually, I didn't totally get that. Can you expand on that? We're living a simulation. Hmm. Well, there's other ways out too. Like let's say that it's possible to simulate a universe, but let's say that in a simulated universe, it's a little bit harder to simulate a universe for some reason. And then there's like this geometric series where like each time you simulate a new universe, it gets a little bit harder to simulate a new one. And so there could be like infinitely many. There may very well be infinitely many, but it's more likely we're in one of the one of the first ones that was simulated than one of the last ones or something like that. I see. Okay, so it's kind of like a stronger thing that like it's possible to do it and then to continue doing it, kind of. Wait, and are you talking about like using language models to simulate the universe, basically, or?
Where do you think this loss of information would come from? Like when you go from like this level of simulation to like the next one? Like, mm, I see. So if you're modeling the universe from which your model comes from, so like a language model learning like the whole corpus of the internet, like that representation is lossy. But here's actually a kind of question also like on that. So if you were to try to represent the manifold of like human knowledge and then kind of like predict like what happens next, right? Like in this soup of knowledge, and you want the agent to like, okay, now what? You know, like does it because it can talk forever. Yeah, like a model could how long does a model go on forever in a way that's like that is um like valuable or meaningful, right? Like could you run an agent forever, like always putting out these words? Um I guess then it would be like maybe time in the universe that would be like the limitation for that. Cause like I guess what I'm trying to get at is that like yes, it's you're lossy in compression, but at the same time, you can also create new universes that aren't necessarily simulating like what you're trying to create, right? Like a video game or something. So like maybe it's like time or like energy. Mm. There is some precision.
I
So,
think
so I'm still trying to understand this connection because okay, so we started off talking about this interesting problem of like no, because I think it's a really good one actually. But I just want to make it like try to make it like crystal clear so I can kind of just like write a note and remember this because I think it's a really important idea. But like the idea of we started with this question of what we know how to do is to model the distribution of natural language that exists. But what we want to do is to somehow model this distribution of good natural language that exists or of given a conditioning on some particular question, say, what are the correct answers to that question? And you kind of put forward that this is like related to the question of related to the simulation hypothesis. And I want to see if we can like kind of formulate that in a very clear way because I think it's a really interesting idea.
I'm just curious. So there are different ways in which we can think about this. I don't think the person who was earlier the speaker is not here, so I don't want to invoke his argument. But basically, I'm looking at this problem in a different way. Do we actually believe the LLMs actually represent what we would like the answer to be, or is it only representing what has been said? How can we predict what can be said? And can we just go through the data sets and just predict what others have said? Rather than actual question should be, is that what reality is, like Yag said. I do not think, even if we span through the history of the internet, all the books, scan all the books that anybody has ever written, the relevant books that is, and all the other data that is available about humans, we would not be able to formulate the model of reality that future LLMs will effectively represent in next few decades, let's say tangible goal of representing what reality is. And the answer is pretty simple to me, is our models only represent what has been said and what grammatically comes next. So it could be a number, it could be a token, which could represent a phrase, but it necessarily does not represent my thoughts. Okay, my thoughts, let's say I'm an agent, I have an agency, I can think about you, I can think about something which is virtual. So there is a basic categorical mistake when we're trying to answer this question: what is real? What is real, as far as the physics is concerned, is very clear. There are two different models which do not talk to each other. One is a very clean block universe type of conceptual classical mechanics, which can actually predict pretty well our three-dimensional plus one temporal dimension space. And our tabletop physics is very well defined for everybody, for us to navigate through our day-to-day life. The other three forces, which is essentially quantum universe, it is very well formulated, but philosophically it's not ready for us to understand in a way that we understand classical mechanics. A very simple example would be the inherent randomness, the Heisenberg's uncertainty principle does not fit in really well when it comes to classical. No matter how many times you write down your differential equations in Einsteinian geometrical way, whether you want to understand them through the lens of Schrodinger's way or through the Heisenberg's S matrix way, it's not going to work. So our basic understanding of what a physical phenomena represents on a piece of paper is incomplete. So no matter what I say, it is going to be a layered way of answering a question. That if I say I love my wife, or if I love my girlfriend, what are you talking about? You're talking about a human being, and then you're talking on top of the human being, you're layering it with a emotion. What are the emotions, so on and so forth. So it's a layered answer. So a physical system answering a question in a language that another human being understands, it's a layered answer. It's not a physics, it's not physics plus philosophy, but it's a language plus physics plus philosophy plus a whole lot of data. So I don't know if we have a model to represent that. All we have are the words and numbers which people have said and used, and we're using those models in a probabilistic way, what comes next. And that is not representation. Yeah, exactly.
So I don't think any data set, like even beyond language, I don't think any data set can possibly represent all of like a perfect world model in full fidelity. But I think what we can get out of a data set is, even a noisy data set is a self-consistent set of relationships between concepts. And I think, there's potentially a lot of such internally consistent concepts that you could pull out of a data set, but probably the largest one that you can derive that's fully self-consistent. And I think we can hopefully hopefully reality
By the way,
itself
Andrew,
is.
do you think we can escape the formalism of Gödelian way? Can we
Wait,
inherently?
sorry, but real quick before we get to that, actually, I just wanted to say I think I've finally understood kind of Yikes' point in a way. In that, if I'm saying it, let me know if I get this right. But I think that I'm understanding, like, the question is, like, let's say that we imagine that if we took a big enough transformer model and we trained it long enough only on human language, with a big enough model and for a long enough time, we'll be able to actually produce true human language, even if the data we train it on includes kind of a mixture of true and untrue things. And the reason that might happen, and this may or may not happen, but the reason it might happen is because we're somehow able to extract kind of the latent variables, which are a representation of, like, the actual, the actual world. And if it is tractable to do that, then that would kind of validate the simulation hypothesis in a way, because just by training on kind of the mixture of true and untrue things that are output by who happens to be here, who are humans, we can create somehow this model we're able to create represents a simulation of the world. Is that the right kind of idea?
Hmm. Yeah, I wonder how much of spatial reasoning is necessary to understand the manifold of human, like, language. Like, you mentioned, like, capturing the latent variables of human language and, like, to generate true human language. Like, I wonder, because humans were born, you know, in our environment, and we developed language through many physical processes over, like, millions and millions of years. So I wonder how much information is missing when purely training on information found on the internet, or, like, I wonder if you would really actually need an embodied agent, like, in the real physical world to. Mhm. Mhm. Oh, yeah, you could, like, you could it's interesting to think about human in like our physical environment. Our physical environment is like relatively predictable, at least from a human's perspective, right? Like if you drop a ball on the ground, it's gonna bounce on the ground probably. You know, if like you open the door, it's probably
By the way, the bounce on the ground stuff that you're talking about, the differential equation to actually predict the trajectory of the exactly where the bounce is going to go, that's very nonlinear, and it is basically it's not a solved
yeah,
problem.
right.
So
But
it's not.
I guess what I'm
Yeah.
getting at is that you have like a physical system and it's relatively consistent. But you can create systems in a computer that are infinitely complicated, or even just with equations.
No,
Like
a
you can say
consistent
something that
system.
is non-compressible to a
I
certain
was trying
degree.
to say was even a consistent system with nonlinearity in it would depend on its initial conditions, and it would be widely different data set would be required to generate the same amount of result that you have already simulated previously. So even the deterministic systems would produce different outputs.
I guess well, I was just trying to tie it back to this sort of like universe thing of like a bandwidth, almost like a bandwidth limitation on um, like how much information you could then simulate. Like, because you can run a system for as long as you possibly can that has like non-compressibility, and you could, well, yeah, I guess you could kind of, I guess what I was trying to connect was like the idea of um, like how much information is necessary to be in a physical system, and how rich our information of language comes from the physical world that we came from. Like even just like sayings or like the feeling that you get when you speak. But mm, yeah, there's like a chemical process inside. Yeah, I think about I just this brought up a great thought. Like, if you were to meet somebody who speaks one language, who has only ever spoken one language in their whole life, and then you meet somebody who speaks like a bunch of languages, the perspective that this one person has on their own language, where they only speak that one language, is so. It has to be like obviously it's different because they're different people. Yeah, like they and I don't like if you've ever tried to study a new language, you probably have ran into this. Like there's like native people who speak a language so natively, like they were born with it. They have like these experiences that that just you don't really ever get to learn as like an outsider. Like you can try to learn as best as you possibly can, right? Um, but there's just like like it goes both ways, right? Like the person who knows a single language for their entire life has a certain perspective that you really can't model with a language with any model that has had multiple languages because like there's some bleed over there of context. And then it's the flip side as well, like the person who has just this one language forever, trying to understand the world from the perspective of somebody who speaks five languages or something. Like it's it's just so yeah, I think the other way around mostly, like, trying to understand somebody who's only ever spoken one language, like, you can't really do that if you've learned the other 5 languages. Maybe you can approximate it, but through general means basically what I'm trying to get at is, like, it seems like specialized systems are almost there's almost, like, a limitation for trying to fully generalize a generalizable model into fully specialized models, you know? Like, I'm sure it's possible, but you would need, like, a whole 'nother partition. Maybe that doesn't make sense.
Yeah, what those guys said in like 50, 55 years ago. So if a lion could speak, we would not understand him. I hope that reference makes sense.
Oh, I think your mic was messing up for the first half of it.
By the way, sorry guys, I got to step out for a few minutes. Yikes, do you have the space for now?
Yeah, I was gonna say I should probably wrap it up pretty soon here too. But if you just a couple minutes, I can hang out until you get back.
Yikes, you there?
Oh, yes. Let me see if I can.
Oh, he might also have stepped out. All right, thinking and dreaming.
Yeah, it took me a while. You're good.
Oh,
okay.
Yeah.
Okay. Yeah, so I'm just gonna be out for like 5-10 minutes, but yeah, you got it.
Yeah, I was gonna say I probably should wrap up and take off here soon, but I can hang out for a little bit. It's all good.
Okay. All right. Well, I'll be back soon. All right.
Yeah. Oh my God, why is this happening?
Yeah, I should probably go also.
We've killed it. We've killed the room. God damn it.
No, you guys can keep talking. I just I haven't showered. I went in like the spa earlier and have some chlorine on me,
Nice.
so I want to like wash that off and
Yeah, fix that world model, bro.
yeah, exactly. Yeah, it was great getting to talk to you.
Yeah, cheers. Yeah, I feel like the definitely like covered a lot of ground. I love me a good book club because we it ends up partially productive and then partially a lot of fun after we all get a little too far into thermodynamics or what have you. Sort of seems to be the case in most.
You know, that rabbit hole where all conversations at the end of the day turn philosophical.
Mm-hmm. Me and my friend had to make a rule of like, okay, the first time somebody brings up the third law of thermodynamics, we have to leave the conversation because we got too many of those, and just like, yeah, you just got stuck there forever and ever.
Yeah, that's a analogous rule. You know, whenever discussing politics, the first person who says Nazi or Hitler, we gotta end.
Yep, absolutely.
What was that server that you mentioned that the Entropics people are in?
They have their like little team server, but they are also in mine, which is I think I have a link on it still. Yeah, it's the link on my profile, just arena.xware.online. You just go to my profile and you'll find it. I don't
Oh,
know if
nice.
they're
I'll check it out.
making the other one public yet. Otherwise, I would share that one. But some of
Ah,
them are in
I see.
there, in which you could, I'm sure, inquire if you were so inclined.
Yeah, that's related to some of the work that I've done. I was excited to find that paper.
Oh, or yeah, as far as I know, they haven't put out any papers yet. What's the related work you're doing?
Um, yeah, well, so I started out, I worked in cognitive architecture for robotics, and then I moved on to autonomous vehicles. Then I kind of, that was more towards the symbolic AI. I essentially programmed a semantic graph for reasoning. Then
Nice.
I took a dive into like reinforcement learning. I read the Sutton book, and there was like tons of bottlenecks. So I wanted to create a framework that was more well-rounded and accounted for like uncertainty. So I eventually I came across the model of active inference and like the free energy principle, and I was kind of contemplating ways of how to integrate like the concept of entropy and like accounting for uncertainty in like reinforcement learning or another agentic frameworks.
Yeah,
Um,
no, the repo is definitely worth checking out. Let me, I'll grab the, I'll throw you in the active chat here. There's one on X too. I don't know, and I don't know if, I don't know exactly what the purpose of Discord is, but I know people have been adding people to the other chat, so I'll throw that one in there. But yeah, it's definitely worth looking at the repo if what you're trying to do is gauge, you know, try to approximate uncertainty, because that's sort of the general principle. Um, but I'm a big when you say the Sutton book, which book are you referencing? I might not have.
the title is just it's like Introduction to Reinforcement Learning. It was written by like Sutton and Bartow, published in like 2020. It's like the main RL book that it's considered like the Bible.
Perfect. Yeah, have you played with Puffer before?
Puffer?
Yeah, it's a reinforcement learning framework from the dude who did. Have you heard of Neural MMO?
I It sounds familiar.
Yeah,
Maybe.
it's kind of a bigger contest of sorts where it's like hey everybody, like grab your agent and like give it some policies and we'll see who wins kind of thing.
Yeah.
And yeah, he is a big reinforcement learning guy, and so he made a library called Puffer that is, I think, basically the goal is to make it to make RL a lot more accessible than it currently is. So it's got like the environments pre-configured and kind of everything already figured out for you. So it's good for like rapidly iterating and
Yeah,
stuff. So,
I've been looking more into like creating like active inference based agents because RL, in order for RL to be effective, it requires like a massive amount of data, which isn't really practical unless you're in a really huge company. Um, so yeah, that's how I've encountered like the more probabilistic machine learning side. There is a Python library called like MDP for programming active inference agents. I haven't I've only kind of like briefly looked at it. I haven't tested it out yet, but there's also like a language called RxInfer in Julia for implementing active inference based stuff. But the tools that implement it are still kind of in their nascence.
yeah, I might have to take a peek at those. The thing that's coming to mind is, I think there was somebody that was trying to do some financial modeling, but with kind of like an RL sort of agent-based kind of framework. I didn't get the chance to check it out, but it sounded pretty interesting. I would, in trying to sort of map one of the interesting things about O1 when I was sort of looking into it, because I was like, okay, I wanna revenge this thing. one of the things that they sort of said was that, okay, well, we started with Monte Carlo because we wanted to sort of be able to spend some extra compute and spend some extra time during inference. But we found that Monte Carlo is really, really good for things like Go and chess, where you have these very clearly defined rules, but it's terrible for things like poker. But what's really good for poker is RL. So that was sort of the angle that we approached it from. And so I'm like trying to find a good way to involve RL in language modeling. And there is sort of like I've hit on a few things, but in terms of like trying to really do it with agents, I haven't really found the thing that sort of like unlocked it for me, I guess.
Uh, yeah, there's one of the branches that I came across in active inference is called like Bayesian mechanics. It's essentially kind of like predictive modeling of like generalized dynamical systems. It's kind of like a more physics based like involvement with the free energy principle.
Hmm. Yeah, I think
Yeah,
in terms of the I haven't really quite mapped that yet onto obviously this is technically the book club is about is about doing the energy based modeling, but I haven't really quite gotten that all the way into my this is how the thingy works model, I guess, quite yet. But the entropy part is the part that I'm like familiar with to some degree. Um, I should. Okay, which one is?
yeah. I took in one of my research quests. I took a dive into how like Shannon and Boltzmann came up with their entropy equations and how they. I was trying to figure out how they defined like microstates, the kind of the context behind that. Um, but yeah, there's still some uncertainty around there. I remember in the beginning of the spaces, somebody asked, like, why is it useful to think about like probability distributions with analogies to like energy and stuff?
Let's see. Yeah, I see on page 206 of the book at least. We have MRFs with latent variables, Boltzmann machines, etc. High dimensional joint distribution in discrete spaces. Let's see. The RBM supports efficient approximate inference since the hidden nodes are conditionally independent given the visible nodes, i.e. math. Note this is in contrast to a directed two-layer models where the explaining away effect causes the latent variables to become entangled in the posterior even if they are independent in the prior. There are words that we went over earlier that are also in there. My brain is about shutting down, I think. Not that it would have been able to handle this in the first place. did it back then.